This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
This week, our speaker is Kevin Hayes from Atheros Communications, a Stanford company, founded by some of the people from here. The talk here is going to cover the need, evolution, and detail for WLAN security. Kevin is a graduate of Purdue. He's currently a distinguished engineer at Atheros, and has a long history of working for interesting companies ranging from Sun Microsystems, 3DO, Epsilon Networks, and I think a few others, where he spent time before joining Atheros. He also has that important and somewhat inexplicable interest in managing the standards process, and he's going to say a few things about that.
Of why I got stuck with it?
Something like that, yes. In any case, Kevin, you're on, and we finish off about 5:30 and leave some time for questions.
Great, thanks. All right, thank you all for coming. Let's see, so I would assume that either in this room or other rooms you've all used wireless LAN before. Most of you have laptops either here or somewhere else. Let me just before we get into the wireless part, let me share a couple things about myself. Right, so I've been working in networking and operating system stuff for a few years now. Networking is now near and dear to my heart. I thought myself to be a layer 3 guy for the longest time, and the question is, what am I doing at a layer 2 company doing software, right? There's lots of people that are my peers there that wonder the same thing. The managers just tell us to keep working. So for the most part, I've been the guy that's been, the sacrificial lamb maybe that's been, for the software point of view that has to or gets to or goes to the meetings for the IEEE. I'll go into a little bit of the context of the IEEE 802.11, but just quickly, I've been or am currently a participant in these task groups. They all have quite different goals, but there's one common thread through most of them, as you'll see that there's some sort of some type of wireless security component, and that's kind of my specialty. I should say also, so if you have any questions at any time, I'd like to make this as as interactive as possible. All right. Yeah. Marketing slide. Wireless is really changing our world. There's lots of devices. There's lots of services, right? So there's CE devices that are becoming important. 40 million is the definition of important. There's voice over IP phones that are becoming important, right? So there's lots of new avenues for wireless technology, right? The services really is, that's another name for how do we bill you for this stuff, right? More of you'll see this service everywhere, but also, more and more accounts. Even so, I live in Mountain View. Even Google, in fact, their free wireless service for Metro Wi-Fi. Well, you still have to, go through an accounting phase. You still have to land on the Google web page as the very first thing you do. Not for security purposes, just or not for accounting purposes, just so they can track things. Okay. Right, and you see other services, iTunes and Rhapsody and so forth. Right. Well, you people are all very young. I can remember when this happened before. I can remember when circa 1994. Not very many people had a web browser. There were a few, some in France and so forth. And really the name of the game was connectivity, right? no one really cared about security at that point, because if you had connectivity, that was the most important thing to you, right? And if you had connectivity, the thing you wanted most is a faster connection. That's exactly where we are today with wireless, right? So with 802.11b, with 802.11a, with 802.11g, with 802.11n, all these things are nothing but faster and faster PHY levels, faster MAC. Right? So this is changing. I should say that what you see today is more than 60%. That's very conservative. I think actually the number is 80, but more than 60% of home wireless networks are set up unsecured, right? And this is not that it's impossible to do. It's just that more and more people in the mainstream are buying wireless networks. More and more people are deploying them, and they either don't want to take the time, or it is rather daunting to look at a configuration page. I have one later, and trying to figure out. So I bought this thing to surf the net, and my daughter said it's what I need, right? So how do I get there the fastest? Well, the fastest thing is to ignore it. Right?
Or they want their friends to use it.
Or they want their friends to use it. Yeah, this is true too.
You want to be part of a pool of hotspots. You don't want to isolate the port into the general internet.
Yeah, I'll get 2 more slides. So let me talk about 802.11 for a minute. So 802.11 is a subset of the IEEE 802. IEEE 802 is really it's an international, they claim, standards body that is responsible for local area networking, metropolitan area networking, and actually personal area networking as well. So they write standards for those protocols, right? Or they develop protocols and codify those as standards. So for 802.11, 802.11 is the wireless component, the local area network. It's very analogous to 802.3, which is very similar to Ethernet, and it uses collision avoidance, which is one of the main differences from Ethernet. It provides acknowledgments for unicast. It doesn't provide acknowledgments for broadcast. These are all just the things that are unrelated to security. Right. One interesting thing is that for most deployments, it uses something called an access point. The access point fits very nicely into a security model. The access point is responsible for forwarding frames from one wireless node to the other, and in fact, it serves as a portal from the wireless, what's called the basic service set, the BSS, from the wireless BSS to the wired or perhaps another wireless network. Right. So really, the AP's job in life is to do transcapsulation, right, and to be a NAS, a network authentication server. Okay. And we'll talk about that more in a minute. Yeah.
Please explain the acknowledged unicast data delivery.
Sure. So unlike Ethernet and unlike most wired networks, there is built into 802.11. There's acknowledgments. Okay. For every data or management frame that is transmitted that has a single destination address as opposed to broadcast or multicast. So those then require, and the protocol is built with this, that there's an acknowledgement, there's an ACK frame that flows in the other direction, right, back to the sender, right. So this is very useful because unlike Ethernet again, so every frame can go out at a different transmit speed, okay, and so you can do things like rate control. You can have a either closed or open loop system that is sitting there and it is watching the ACKs come back, and in fact the ACKs have to come back within limits. They have to come back at the same rate that it was received at, right. So this tells the transmitter, so I didn't get that ACK, so I'll retransmit at a lower rate and see if I get that ACK, right, and so this becomes a closed loop system. This is, of course, very hard to do with broadcast, because you send a broadcast frame, you get 30, 40 ACKs back, and what do you do with that? So the IEEE just kind of threw up their hands and said, well, we won't do anything with that. So we don't require ACKs for broadcast and multicast. Okay. All right. So you'll pardon the klutzy engineer animations here, but all right. So this is the access point. right? So what we're building here is a basic service set. This is one device that we all know and love. This is a laptop. We can do streaming perhaps on some other device, and concurrently we can have a voice call, right? And you can have multiplicity here and dozens of devices. Once again, the access point clearly serves as a portal to the wired network that you would kind of logically think is there on top, and it's a very good point of enforcement for the security. Okay.
The issue here is trying to provide a large amount of bandwidth to a large number of devices, and at least with some of the 802.11 protocols like 802.11b, the number of devices is extremely small, and the bandwidth that it's able to support is actually quite low.
Yeah, I guess I'll challenge your first assertion that the job in life is to provide lots of bandwidth to devices. There's two devices. Well, right, one device here that really requires very little bandwidth would be the voice, right? The other two, okay, fine. They can benefit by all the bandwidth you can give them. The voice. So there's actually one of the subgroups of the IEEE, the 802.11e group has now defined a QoS protocol that the access point and interested clients could participate in. So, for example, the voice guy walks up to the access point, right, and he would have an exchange with the access point, and his client would say, you know what, I don't really need a lot of bandwidth, but here's my traffic spec. Here's what my application is going to look like. I'm going to give you a packet every 50 milliseconds or 20 milliseconds. That's that's all I want. You make sure I get that, and I'm happy, right? So that's one difference. Another difference is, your case of the 11B actually is an interesting case, the 802.11b. For 802.11b, let's say, for example, that the laptop was in fact an 802.11b client, right? And let's say that everybody else in the network was running 802.11g, or they supported it, right? So now the access point, when he allows that first connection, the access point has to say, okay, life has been good so far, but our life is now no longer good. Now everybody, when they transmit a frame, they have to send what's called a CTS to self, right? A clear to send, and basically spoof. So you have to spoof the 11B guy to think, okay, no one transmit for now because I'm going to do this OFDM thing over here, right?
Well, let me give you an example. I don't want to divert you too much, but high school classroom.
Yeah.
40 laptops and lunch hour.
Yeah.
And that's another 60 or 80 laptops within range. So you have one access point trying to serve reasonably something on the order of 100 users.
Mm-hmm.
The system dies. Performance gets to be just terrible.
Mm-hmm.
Everyone thinks they're getting a lot of bandwidth, but it turns out they're getting virtually none.
It's a shared medium.
That's true.
Right.
And it's very difficult to characterize and very difficult to understand what the actual performance you're going to see is.
And very difficult to write system software that scales to that amount. Right. Agreed.
In any case, we'll take this offline, but it's just an interesting...
That's a good point. Yep. Right. So, what I mentioned before that we were in the era of like just connection. So what does this mean? What are the risks that you can take? Well, many of these are just generic network security, perhaps network hygiene issues, right? Certainly file theft. You run your file sharing protocol either intentionally or by accident because you didn't know better, right? And this then leads to identity theft or possible identity theft. Insertion of viruses, depending on if you have Microsoft sharing on, right? And these are files that get transmitted in one way or another, and they are doing various things, and the user could trip on this file. If it's called setup.exe, they're likely to double click on the file, and boom, you have a virus, right? So these days there's rootkits, there's zombie daemons, and so forth that get used, right? So all this is this is all well and good. What do we do about it, right? So I think there's an issue here that users don't expect that when they go out and so last year they bought a wired hub or a wired switch, and they didn't have to think about security, and now they go out and buy one from the same company, same color, and it has this little antenna on it, and now they've got to do a bunch more stuff. Well, that's a sad fact that wireless has a different usage profile, but nonetheless, what is it that builds the security? Right? So it's really for network security, it's really built on three things. Right? We have authentication and key management and confidentiality. For authentication is really what the TSA has to do every day, right? So just because you are holding a boarding pass, how do you know that you're the person that's actually supposed to be on the plane instead of the person that just found the boarding pass in the airport, right? Right, and so you want to be able to prevent the unauthorized user from being able to write into the network, right? That's what authentication gives you, right? And it's not, so this is different than crypto. This is, you could do authentication, we'll talk about it in a minute. So you could do authentication with no crypto, and that's even useful in some circumstances. Right? Okay. Key management. Well, this is very important. This is really where the main point where WEP really fell down, and we'll talk about that too. This is an agreed upon secure way to manage, and that means to derive, distribute, or utilize a secret. All the security is built on a secret, whether it's derived or whether it's implicit. If it's implicit, you don't really have much security. But the key management is how you deal with that secret. Who gets to touch it? Who gets to earn the right to share that secret? Okay. And a very important property here is that you can have the most secret system in the world, but unless there's causality, right, then it's useless. So if I have a session that I want to set up with somebody, if that session was reused or was used by somebody else in the coffee shop 10 minutes ago, what good is it to me? It has to be dynamically set up. It has to, and to build this, I have to give you something. You have to give me something. These are often nonces. Right? Okay. Okay. And finally, the confidentiality. The confidentiality, once you have the first two, the confidentiality comes for free thanks to mathematics, right? And you've probably heard about public key encryption and other forms of encryption. This is, pardon, but it's just encryption, right? There's all sorts of block encryption algorithms, stream ciphers, and so forth. This is, out of all the standards, this was the easiest part. And that said, it was easy because somebody else had already done it, So this. Ciphers then prevent unauthorized people from being able to read what you're sending on the network, right? So, one of the cryptologists once told me that, in terms of authentication and confidentiality, given those two rules that one guy can write into your network and the other guy can read from your network, which one would you rather prevent? It seems like to me that the authentication is very important. It seems you want to be able to prevent that guy from being able to write $10 million into his bank account, right? If he just sees that somebody transmitted a packet that said, oh, $10 million is going into that bank account, well, okay, so now he has to learn the bank account and how to attack that. But if he can actually write something into your network, this is a much bigger deal, right? So you have to have really all of these, right? I mean, so otherwise, you really just have this situation where you have like a screen door in a submarine, right? You say, okay, I'm going to shut this hatch, I'm going to shut that hatch, but you have to have all these. Otherwise, you really have WEP, right? WEP was the wired equivalent privacy, right? It was the attempt by the IEEE to have some modicum of security because I think they got told that they had to have it. So nearest I can tell, there were kind of some junior crypto guys that kind of were in the back room, and in the course of one weekend, they said, oh, RC4 is a good cipher, we'll just use that, and everything else will just work. No, it works exactly the opposite. The cipher is the least important, right? So it was designed bottom up or bottom whatever. Right. So and in fact, a very good example of this is what WEP calls shared key authentication. Okay? Shared key authentication is when, you wander in range of some access point and you say, so I have a key, maybe he's got my key. So what I'll do is I'll send him a message saying that, kind of a knock knock, hey, I want to come in. The access point then sends you something in the clear, totally in the clear, right? And it says, okay, so I'm going to challenge you, right? So you take your stream cipher and you encrypt this message and send it back. So what's the attacker got? Well, let's see. Attacker's got clear text, the attacker's got cipher text that exactly matches. He knows this thanks to the protocol. So he XORs these together and he can get that much of the key stream, right? Through 2 packets, right? 2 packets that are the very first packets that are always used, when the client comes within range of the access point. This is just junior crypto, right? There's no per packet authentication. There's a key hierarchy, which we're going to talk about in a minute. Every packet that gets sent with other algorithms has some sort of a message integrity check or a message authentication code that can be tracked to the basic authentication that happened as the very first process. The 802.11 frame header is not protected by WEP, right? So you've got 24 bytes of unprotected data. You can play games like, I don't want to send this frame to that access point. What I want to do is I want to capture that frame, just kind of scribble over the MAC address, send it over here, and see if that access point uses the same key. My God, right? So how long did it take to figure this out, right? So there's actually no replay checking, the same thing. So you could, so an attacker could capture any frame off the net, perhaps the frame that says transfer $1 million from there to there, and replay it. And unless you have some layer 3 protocol, then the system's none the wiser. There's no liveness or causality, as I said. So there's no session setup. The keys are all installed a priori. You have to know the keys. You probably got them in an email message that's laying about, or a post-it note from your admin. There's no auto negotiation in that sense. Right? Okay. And once again, RC4 is a perfectly good cipher, but it does have some areas of weakness, which were pointed out by a couple researchers. And in fact, how WEP just decided to set up the cipher, well, it does expose that there's a weakness in the first 256 bytes of the RC4 cipher. So you'd say, okay, fine. Well, the first 256 bytes of the key stream, that's fine, right? Most sessions are longer than that. No, they restart the RC4 engine for every packet. So guess what? Every packet has this weakness of the first 256 bytes. So, all right, so that's WEP. So you think, well, gosh, it's layer 2 security. Who really, that's kind of rinky-dink, right? Why would you do layer 2 security? Why don't you do layer 3 security? IPSEC is where it's at, right? Well, no, not all the time. I mean, part of it, quite frankly, is just the sensibilities of the groups that are working on this, right? As the layer 2 guys say, well, I have this layer 2 problem that I kind of created myself, so I want to solve it here. And the layer 3 guys are saying, well, you got that layer 2 problem over there. Don't come talking to me, right? That's in fact part of it, but there is more than that. We live in an IP world, but gosh darn it, there are other layer 3 protocols. Not many. There is old Apple Talk. There's IPX. There's SNA and things. And granted, they're kind of going away, but there are other layer 2 protocols layer 3 protocols than just IP. So to apply IP to solve all of the other protocols would not be appropriate. And in fact, when you think about it, well, let's see. So I'm bootstrapping my connection. All right. So I walked into the coffee shop, and I need some resources to be able to do anything at layer 3, right? I need an address. Where am I getting an address? Well, I get it from a DHCP server. DHCP server. So I talk to the DHCP server with no security. Well, I could just kind of invent an address with auto IP, and that might work. So why bother with all these layer 3 resources when we can do this at layer 2? Layer 2. Well, what does that mean? Well, layer 2, really you're talking about port-based security, right? Think Ethernet switch here, of an array of ports, 48 ports or whatever. And, you want to be able to come up, or the model in that, so the model in those days was to come up with your Ethernet jack, your Ethernet wire, plug into a port, and do some sort of protocol that authenticates you to the network. Notice I said authenticate and not crypto here, right? Because at that point, there was deemed to be no need for encryption. And so you saw that there was a genesis of things that came out that were authentication only, right? So they would just make sure that you are who you say you are. After that, it's free love, baby. Come on in. Yeah, okay, so I trust you now. Come on in, and you can do anything you want. Right? All right. So what is port-based authentication? Well, it's we have to take a little bit of a trip back and to think about how PPP came about. Right? Well, PPP came about because there were these banks of so everyone connected over a phone line. They were running serial, over modems. The modems then were aggregated. These things were aggregated into a NAS. The NAS was the network access server. The network access server was a point of enforcement. Sounds like an AP. And and from that point, then they were sent. The session was sent upstream to a AAA server, usually Radius, and so there was some session that was sent end to end from the Radius server to the person at the other end of the line. Right. Well, these protocols that were used, PAP and CHAP, the password authentication protocol, and the challenge handshake authentication protocol, right? So these began to proliferate, right? Just 2 here, but I think there's over a dozen, right? The problem was that every time you did this, you had to burn a new version of PPP, right? And they would auto-negotiate, this is true, but people began to say, well, why don't we kick this authentication thing out of PPP and have some extensible authentication protocol, right? It's all well and good, So we're still, back in the days of modems, we're still like, okay, EAP, great. So now I can run just PPP for a transport, right? I don't need my PPP to be my all singing, all dancing protocol anymore. It's not doing security. All it's doing is encapsulating my EAP, right? Well, in fact, EAP is an RFC. It's managed by the IETF. I said it's encapsulated in PPP, but in fact it's encapsulated in IP, usually, right? So there really was no direct IEEE 802 encapsulation until you had a protocol like IEEE 802.1x, right? And this was the first time that you had a consideration of, okay, so I've got a port, so I've got a LAN now, and it has a series of ports. So what I want to do is to modulate those ports, is control those ports, and to have a port access control protocol, right? So that I have to have some way to authenticate, and optionally to exchange keys for key management, and then optionally, if I have keys, I may as well do crypto. So I have the 3 basic tool sets with 802.1x, right? So the marriage then of 802.1x with EAP, this really built a very powerful system for layer 2. Even though EAP was in fact, it's under the charter of layer 3, it's under the charter of the IETF. Okay. So EAP, right? So there's now dozens of methods to do EAP. One interesting one here at the top, EAP MD5, in fact, is a useless protocol for wireless because it's a very good protocol for doing authentication, but in fact it is not capable of deriving keys, right? So it can do authentication, but you wind up with no cipher. Okay? So for wireless, this is just not a good idea. For the rest of them, though, you can always run. So when they complete, you always have some form of authentication, either 1-phase or 2-phase, and you always have some keys, I don't want to call it residue, but something left over from the protocol that is sufficiently random and agreed upon that these can be used as keys. Right. So at this point, are there any questions? Have you seen? I doubt that around campus that you really use much EAP. Is that true?
I don't know.
Are most of the access points open? Right, so for enterprises, the most popular EAP methods for enterprises, you might guess, happen to be, they happen to be what get installed by default on the servers, on the back-end servers. Many people run Microsoft servers on the back end. Microsoft wrote the EAP-PEEP for both TLS and MS-CHAP v2. Those happen to be a couple popular protocols. Imagine that. There are other companies. The TTLS was written by a gentleman at Funk Software. It is very similar to PEEP, but it's kind of an early version, and it is a multi-stage protocol. So it requires that there's PKI in the first phase, but then no PKI in the second phase. Okay. All right. So this is kind of funny. I don't have a laser pointer here, but you can see the. Okay. So I got this off the web, and it's a good enough diagram. This is actually going through the OTP, one-time password, right? So it's very simple. There's a EAPOL start message, which is actually a different protocol. Is EAPOL. That's EAP over LAN. And then there's a request response of the identity, and then it launches into the OTP, the one-time password challenge, and the response, right? So also some assembly required. Hang on, the battery. Please, battery. Great. Thank you. All right. So I got this off the web. I can't figure out what this is here. This looks like a stack of bills to me. Like the guy paid $50 to his admin to get in or something. I thought, oh great, this is the canonical router thing here, and I had it on the page, and of course I can't erase it, but I figure that this must be some sort of social attack, right? That the guy's trying to show. But, all right. So once again, basically you have the port authorized here at the bottom. Keys are going to be exchanged, which are not shown here. We'll get to that in a minute. And at the end of this session, whatever the session is for, there's an EAPOL logoff, which is sent from the client to the access point. It should be noted, that the authenticator, there at the top, the authenticator often runs in the context of the access point. It's often a radius client, or I should say, it talks to radius with a radius client, and it talks to the station with a EAPOL server, right? But it usually runs in the context of the wireless access point. Right? So I talked before about how do we get linkage? How do we prove that? Okay, fine. I gave you whatever certificates were actually needed. Now I send you a bunch of traffic. What does that mean? I mean, how can you be convinced that outside of just having a key that only you can decrypt, how can you be convinced that it's really me that's sending every packet? That's non-repudiation, right? Okay. Well, so what we do is we build a hierarchy, right? And we start out with a master key, which is derived as a part of that radius server transaction that was there before, right? From that, we build a pairwise master key, which is basically a one-way hash from the master key. Okay? And from that, we build a pairwise transient key, and that is made up of 3 subcomponents. There's a key confirmation key, right? You can see them here. The EAPOL encryption key, so that later we can, in the next frame, I think we'll see that we're going to send some keys across the link with EAPOL. And finally, the transient key. The transient key is literally what gets stuck into the hardware, right, for the cipher. Okay. All right. So the AP for the transaction that I showed with the EAP, the AP really hasn't been a part of this to this point, right? The AP has been a tunnel. We started out, and the station sent a EAPOL start, and from that, the AP did actually take some action, which was to send the request identity. After that, he's a tunnel. All he's doing is transcapsulating from EAPOL, from the station, to radius for the authentication server. Right? So he after the radius completes, he doesn't have the key, right? He's oblivious to this. He has not been privy to this conversation. And you can say, well, he's a man in the middle. He is indeed a man in the middle, but he's a man in the middle by design, right? In fact, he will be trusted at the end of this process, but what we're going to do is we're going to give him a key first, and then the station, who doesn't have to trust the AP, is going to walk through a different protocol to find that the AP has the same key that he has, that the station has, right? Okay. All right. So how do you build that trust, right? So so you have to be able to exchange some kind of dynamic data, right? You have to. So we're going to assume that that the other endpoint doesn't trust its peer, but we're going to have some exchange, and we're going to have some result which is predictable that the other endpoint can wind up trusting the first endpoint. Okay. Okay. So this is what we see, right? The 802.11 association. This is the point at which you just walk up to the access point. There's really no there's no security here other than just negotiating capabilities. The access point will advertise its capabilities in the beacon. The beacon's sent every 100 milliseconds or so. The station then sees that and says, oh, okay, so here's a secure access point. I don't know what its key is, but I like security. I'm going to come up here and I'm going to ask him if we can walk through security together, right? So they will go ahead and do the 802.1x, and from a couple slides ago, we see that there's a master key that is going to be built, and now we're going to install or we're going to derive a pairwise master key on both sides, right? And now the challenge is to see if we can make sure that those are in fact the same value, right? So what we do with message 1 here, with M1, is in fact that there's a frame that's sent from the access point to the station, and that's really just a nonce. That's just what's thought to be a globally unique number. It is certainly session unique number, and it's sent from the access point to the station with no crypto whatsoever, right? So there's it's not authenticated, it's not encrypted or anything. Message 2, so in response to that, now the station has the nonce from the access point. He can create a nonce himself. Once he has both those nonces, he can string those together and hash those with that PMK, and that becomes essentially the MIC for this frame, right? So the MIC is now related to something that the access point gave and the station gave. This is liveness, this is causality, right? So now he sends that frame, M2, back to the access point, which knows then to trust this frame because it has a MIC. The access point then obtains the station nonce, and then he will send the message 3 back. So message 3, depending on the version of the protocol, message 3 will have the group transmit key. We mentioned before that there's there's different services for unicast and for broadcast/multicast. The group transmit or the group transient key is in fact what you would do, what the AP is going to use when he sends out broadcast frames. Okay? And finally, there's a protocol acknowledgement. And the last 3 frames are mixed, as you can see. This is really what 802.11i, the security subgroup of the IEEE, this is what we call the 4-way handshake. Right? And this is done every time you authenticate with any access point that's running any non-WEP security, really. If it's running a pre-shared key protocol, which we'll talk about, then it'll only do this, right? So it already has a PMK in that case. But if it's using 802.1x, then it has this design that I just lay out here. Okay. All right. So back to ciphers. Right. So how did the IEEE fix the hole that was WEP? Right. So there was a lot of pressure to do something about WEP, more than just say it's bad. And so what some vendors said was like, well, gosh, we have all this RC4 hardware that's already deployed. We'd really like just a firmware patch to our access points, kind of ignoring the fact that grandma would never install a firmware patch. But they said, okay, so we need this firmware patch that we can use our existing RC4 hardware, right? So that's what happened. That's what TKIP is all about. TKIP is a upgrade, it's a patch, and it really was not designed to have a very long lifetime. It's said now that we're well into, we're well past the half-life of TKIP. Right? Its days are numbered probably. Okay. It uses key mixing. The WEP standard only allowed a 40-bit key and a 104-bit key, and so to reuse that hardware, you wind up with a 104-bit key per packet. But thanks to key mixing, that winds up being 128 bits across your whole stream, the set of all the packets that are used with this key. And there's WEP had a 24-bit initialization vector. The initialization vector is that thing that I talked about that actually got prepended to the key stream. And so TKIP does this. So TKIP does the same thing, but it performs this operation as part of the key mixing, which is done as a first step before sending things to the WEP engine. Okay. Also, one of the things that WEP did wrong was the wrapping of the IV space. 24 bits at 802.11b rates. That took a while, but it doesn't take nearly as long at 802.11a or 802.11n data rates. Right? So 16 million packets, you can kind of sit there for a couple hours and watch all the traffic. You can see it all, right? So with 48 bits now of IV space, this is, you would be very, very old, very, very, very much in the ground by the time you saw 2 to the 48th packets go by. Replay checking. WEP didn't have any sort of replay checking. TKIP has replay checking by watching the values of the IV, the values of the initialization vector. These are prescribed that it has to be monotonically increasing from the transmitter to the receiver. Okay.
What do you mean by RC4 hardware? Do you mean that is implemented in hardware, or do you mean the boxes that have firmware that?
Yeah. So it still uses RC4 hardware, right? TKIP does. And what so RC4 is just a stream cipher, right? So some vendors had implemented just a block. I shouldn't say block. A bulk stream cipher, right? So you would put, you would feed things one way and you'd get encrypted stuff out the other way, and there would be no setup for it. So you would have to install and build the key yourself, which as I say is to build this IV plus the key stream, right? Put that into the cipher engine, right? So those vendors, or some of those vendors, wanted to preserve that capability to basically have a layer above that cipher, so they could still use their hardware engine, right? TKIP these days is often done in hardware. I mean, it almost has to be, right? AES is always done in, well, it's often done in hardware as well. But at the time, in circa 2003, it was still not clear which AES was going to win the day. There were multiple block ciphers that were under consideration. Right? Okay. Well, how's this work at home? Of course, everyone goes out and buys a radius server, right? You hook up your radius server. You run EAP PEEP, right? Because Microsoft sold you some radius server. No, right? So you go and you want to be able to configure this thing quite simply. You want to be able to say, okay, so I've got my little secret, right? And I put this on all of the equipment that I care about. So the IEEE provided for something like this. This is pre-shared key. It's kind of a misnomer. There's really two modes of operation of it from a user interface perspective. Is that if you so for most of the user interfaces, if you enter something that is less than exactly 64 characters, then what will happen is that'll be interpreted as a passphrase. So that ASCII string will be then hashed as a passphrase, right? If you insert exactly 64 characters and these things are hex characters, then it's taken directly as a hex key, right? No derivation. So this takes a long time to type those hex characters, or cut and paste them, whatever. So in fact, this is what we see in FIPS 140-2. You take oh gosh, the pre-shared key thing is not all that secure. Well, I mean, it actually can be, because after you get past the fact of easy password attacks or dictionary attacks on a passphrase, after you get past that, then you say, okay, well, you know, I'm going to take this thing, I'm going to build this key hierarchy that I already put up here. So now my cipher is going to be just as secure as that key. So, you know, if you're FIPS, so if you're the government, you're saying, okay, so, you know, so we can combine this with a secure key generator, right? That take a long time to type in those 64 characters, but once you've done it, then you're done, right? And there's no radius involved. Frankly, I think part of the reason was that they didn't trust EAP at the time. I think, you know, perhaps the times have changed as well. Right? So as I say, you know, this is a double-edged sword, right? You know, if you just type, you know, PASSWORD, well, guess what? You know, you probably don't get a lot of security. If you have 64 characters, then you can get a lot of security, but usability becomes a problem, right? So there's this other standards group called the Wi-Fi Alliance. The Wi-Fi Alliance is largely a marketing organization. It's a trade group, and they had already come to the point of writing many of the test plans that are associated with IEEE standards, right? So 802.11a, 802.11b, 802.11g. The Wi-Fi Alliance already had test plans that test all these things for their PHY and their Mac interoperation. So there was a lot of pressure in 2003 for them to come up with a security standard, and that's what became WPA, the Wi-Fi protected access, right? That's really the moniker for everything I've described so far, except for the AES. The AES came in a later version. Right? Right. Well, that's all well and good, but still having to go and touch every device and having to go and program the password into every device, this is still a drag, right? So grandma has to come in and say, oh, you know, I bought this new digital camera. Let me find the menu item, you know, of where I plug in the SSID to get on my wireless network. What's that rascally key? Let's see. Oh, wow, you know, this thing only supports WEP, right? So this is still a problem. And what was decided was to have a protocol that the Wi-Fi Alliance calls a SimpleConfig protocol, right? It really so it was a bake-off between a number of protocols. 9, I think it was, and there were protocols that vendors had already deployed. What's going on now is that there's a new protocol that has been designed, and the certification will open up presently within a few weeks. Okay? So this protocol gives the illusion that there's really only 2 agents, right? So grandma brings her digital camera home and wants to print out a picture, right? Perhaps the printer is already authenticated, perhaps not. But what she can do is she can really operate these 2 devices and just touch those and not have to say, okay, so where's my access point? I have to go, you know, hook up to the access point first. Okay, so now my printer over here, right? You know, that's not intuitive to grandma, right? So this allows you to use the AP as a transport and really focus on the application. Right? So this then defines what's called a registrar, the enrollee. The enrollee is, of course, the new client, the new agent that is trying to get on the network. And the default level security is set by the vendor, right? So there's a long story in this. I'll make it short. There's a pin, there's some identifier that would be associated with the equipment, and that would usually be associated with the enrollee. If the registrar has some UI on it, keypad, then he could enter this PIN number, and voila. You know, if you know anything about Diffie-Hellman, you can then say, okay, so now I have my shared secret. I can then jumpstart that, use that to authenticate my Diffie-Hellman, and it's all good, right? Well, if you don't, if your application is such that you just really don't have any UI, like I could think of maybe a NAS box, right? You know, a wireless NAS box. I bring it home. It has a power switch, and it has, you know, if it's wireless, it has a power switch and it has a plug, and that might be all, right? Well, okay, so let's say it has one button, right? One button for configuration. So in that case, then I might say, okay, so I want this thing to talk to my access point. My access point might already have a button. In that case, then basically the protocol runs in the same manner, but it says, well, okay, the pin number is equal to 0. Right? So there's no real authentication. This is true, but it still runs Diffie-Hellman. It's still not susceptible to passive observer attacks. So it's more than what you had before, and it's a lot easier to use.
What does the button do?
So the button just basically, the button would initiate the protocol, right?
And you press them simultaneously.
In sequence. Walk over here to the access point, or walk upstairs to your access point, and then walk downstairs to the printer, right?
And
In 2 minutes or less, right?
Hope your neighbor isn't doing the same thing at the same time.
Exactly. If that was important to the manufacturer, let's say a NAS box, then he should have installed the, put a yellow sticker on the device saying, here's my PIN, go and type that into your Windows platform or Linux box, whatever that supports this protocol. Okay. So another corny animation about how this works, right? So here's an access point, here's a registrar, right? What we're looking at here is now, this is the out-of-box experience. This is the first time, this is a Christmas morning that, so you got your PC, you got your access point, and you're not sure if you need to press buttons or what, right? So we walk through here. There's a discovery process where the PC finds the access point thanks to the access point's beacon. I guess it does imply the access point is on in this case. So there's a discovery. The PC then says, okay, fine. It'll have a UI that pops up. Say, dear user, please go read the PIN on your new device, right? It's not even important that it's an access point at this point. So there's a UI that comes up and say, okay, fine. So my PIN is this. I type that in. Next, right? So now what have I got? Well, the access point knows its PIN. It's burned into his flash, okay? And the PC now knows the PIN, so that's thanks to some transport that says someone typing, right? There's been no transfer of the PIN here over the wireless channel. This is an out-of-band transfer, right? Because what I've done is I've used my eyesight to say, okay, PIN's over there, now it's here, right? So that's really the critical part. I mean, after that, the protocol is easy, right? So from that point, there's a registration protocol that runs, which is Diffie-Hellman, and then finally the registrar, who is the ultimate keeper of the network settings, sends those network settings to the access point. Well, what are those network settings? Well, today it's things as simple as the SSID, like the name of the network, grandma.com or whatever it would be, and the key, right? The pre-shared key, which is independently derived as part of that Diffie-Hellman process, right? So that's what's sent today is basically the name of the network and the key for the network. But you could certainly extend this to other settings, like if you're using DSL, a lot of times there will be a PPP over Ethernet that has to run, right? And so you can plug in that password there. There's other things like the extent of your DHCP service, where you want your NAT addresses to start. So all this could be done from the registrar and then sent to the access point. Okay. Right. And then finally, the access point would often reboot, or he would instantiate those network settings, and the station or the client then says, okay, fine. So now I'm going to act like this is a brand new network that I've seen before because I gave him the key. It should be this. He tries that key, and if everything works, it works. Okay. So that's kind of the state of the art today. Chuckle, chuckle. But there's other things that are coming out to improve this situation. Right? There's a task group called 802.11 TGK, which is slated for radio measurement. Right? They've gone through a few letter ballots and so forth. It is an enormous new set of protocol intrinsics, but in terms of security, there are a few things that are interesting. One is AP neighbor discovery, right? So if I'm AP number 1, I can tell you about my nearest neighbor APs, right? How that gets populated is kind of out of band. Your admin might have to go out and literally, telnet to every AP on the planet, who knows? But but there is a way that a client can find out about the other APs on the network without having to go off channel and scan for them. When he has to go off channel and scan for them, this is at odds with throughput. Right? So you want perfect knowledge of your surroundings all the time, but you want perfect traffic. You want to be able to send at the highest bandwidth, and so these are often at odds. So having TGK will let us be able to have a situation where the access point makes assignments to the various clients. The access point goes out and says, okay, so you tell me about channel 1, you tell me about channel 11, you tell me about channel 6. And all these packets come back to the access point, who then does ranking and stacking and says, my life is really hard on channel 1, so why don't I move to channel 6, right? So he then could change his beacon, saying, okay, so we're all going to move to channel 6 now, right? And all the stations would follow him, right? So this would be a scanning enhancement, essentially, right? Another thing is that the AP could say, okay, so here's these 5 APs that are around me, but only one of them supports the security that you're really interested in, right? There's bits in the discovery or in the advertisements that say, okay, so this guy's security is like mine, this guy's is some other thing. So the station then could say, great, I don't even have to go scan there. I don't even have to go off channel at all. I can just use this data, and then to be able to go from access point 1 to access point 2 even faster, which is a great segue into TGR. The fast BSS transition. This is, by all accounts, this will probably be used mostly in an enterprise. It's thought to be a good thing when you're using a device that looks or smells or feels like a phone, that your calls don't get dropped when you walk around. So what happens is that if you're not running any security, this is pretty easy. If all you have to do when you walk from access point 1 to access point 2 is to send an association message and the access point says, sure, come on in, so that's not much overhead. The problem is when you get back to that 4-way handshake, or when you get back to that whole 802.1x thing, perhaps 15, 20 frames, now you're talking about some real overhead and trying to do crypto and trying to derive these authentication mechanisms in real time while you're doing the call, and perhaps just at the limit of the range when you walk from access point 1 to access point 2, things might be bad for you. So if you're at the limit of the range, the performance is the worst and the latency is the worst. Right? So that's what TGR is trying to solve.
Transportable across that.
Transportable sessions, right?
Yeah.
Right. Basically you're trying to use a layer 2 service to give you good layer 3 session, right? And and this is not a session in the concept of in the parlance of TCP necessarily, right? Could be RTP, could be it could be a stream of UDP for all we care about, right?
It's got encryption and a whole bunch of other things
At
along
layer
with
2,
it.
yeah. Well,
Layer 2.
yeah, it could also have a layer 3, yeah. DRM and yeah.
Secret has to go along in some sense.
For the layer 3?
For the layer 2.
Well, I see. Yeah, perfect. All right. So for layer 2, yeah, actually, so what happens is that we independently derive on AP number 2. There's really 2 ways to get there. One is through your current AP, and thanks to the magic of LANs, you can. It's one broadcast domain, so you can you could literally send out a broadcast packet, and it would probably arrive at the other AP. There's some cost to that. As I said before, that's not acknowledged, so it's not as reliable. And of course, everyone would see it, and it would bog down the network because it's broadcast, blah blah blah. Right. So what happens is that it's responsibility of the station or the client to go out and find the address of AP number 2, so that he can use that in a unicast frame from the client. And I wish I had a drawing here, but from the client through AP number 1 over to AP number 2, right? So basically, what he's doing is he's trying to run this 4-way handshake that I put up, 4-way handshake over the wire, okay? So the first hop is over wireless, but then it goes from AP1 to AP2 usually is over a wire, right? So as you say, now I can use that and I can build both my master key, my pairwise master key, and my whole key hierarchy in preparation for, boom, just going there. That's what TGR is doing. Right? So it does build it dynamically. It builds that secret again. It doesn't take that same secret. Or I should say, not all of the same secret. There are implementations where the key scope is in fact different, and that's what I mentioned here, I think. I guess not. All right. So there's others too. Right. The TGS, they just got a really hard job, man. So think about the case of, I'm sure you've seen ad hoc routing and mesh routing and so forth. I mean, it really makes my head hurt. And trying to map security on top of that, and this grand hand wave that the IEEE made at this point that I mentioned before, where the radius server just kind of says, well, I know you don't have the key yet to the access point. It says, here's the key, and then the AP and the client challenge each other. This is all well and good in an enterprise, but try and think of that happening on a light pole, right? From light pole 1 to light pole 2. Where's your trust, baby? And so this is really hard. I have a lot of respect for the people that are working on this, but I'm not sure when it's going to arrive. So there's other things too. The TGV is working on, TGV actually was, all the work that's being done inside TGV was in fact done initially, that work started in TGK, which was radio measurement, and then they figured out that the job was just so huge that they forked another group, and that's what TGV is, right? So the thing that's interesting about security for TGV is that, so once again, take you back to an enterprise setting. So I open the lid of my laptop on Monday morning, and something weird happens, or I can't get authenticated. And so first thing you do is you call support. Well, the first thing that they do, is say, okay, so send me some sniffer trace. A what? Sniffer trace. Well, how do I do that? Well, okay, you run Ethereal maybe, but that doesn't work for your finance people. So what you can do is you can automate this, and you can say, well, okay, so on my back end is going to say, okay, I have this this testing AP over here. That's maybe I deploy one of those on every floor or something, and whenever you authenticate to that guy, the backend server or the backend process always gets every packet that is sent there, and so he can try and help you, right? So what TGV has is this mechanism now is that you can send a frame to the station and say, okay, I want you to go over there to that network, try and get on, and I'll be watching, right? And I'll help you from there, right? Not deployed yet, but this is interesting, right? And TGW is working on security for management frames. Most every frame that I've talked about so far has been a data frame of one form or another, with the exception of if you remember the association request, association response frames. That's an example of an 802.11 management frame. Well, if you're sitting there with you've done all your authentication, all your security, you're doing crypto, you're having a good time. Now some attacker comes up and sends your access point one frame, a deauth frame, and it's not encrypted. Boom, you're dead, right? Boom, your session is gone. You can come back. You can send your 20, 30 frames for EAPOL or for 802.1x. You can have a good time. But this is a clear denial of service, so that's what TGW is chartered to solve. Other things, there's a sub-protocol called direct link setup. This was, I say it's a sub-protocol because it came in as part of the changes for the QoS for 802.11e. Right? This is really where you say, well, you know what, BSS are really cool. I love being in a BSS. I get services through my BSS. But I don't want to have to relay all my frames through my access point. I want to be able to send my, I have a media streamer. Let's say it's a TiVo machine, right? So I have my TiVo machine, and I want to be able to play that on a wireless TV, right? And so, sure, I could associate my TiVo to the access point, send every frame that the TiVo sends through the access point over to my TV. Now consider the case where the access point is in your den, right? Yeah. So the access point is in your den, and the TiVo and the TV are right next to one another. There shouldn't really be so it shouldn't really be a need to hop to the access point and back, right? So that's what four TVs. How many are wireless though? I mean, yeah, so none of them have a network wire. And then also virtual AP. Virtual AP can be, as the name implies, you can simulate the presence or absence of a BSS with some cute hardware tricks, right? What's a BSS to a client? What's a BSS after all, right? Well, it's somebody that's responsible for sending out beacons, somebody that's responsible for sending you management frames, somebody that's responsible for your security, right? And for giving you data service too. So as long as you can get your hardware to do that kind of stuff, you can have deployments then where you have like one access point that to every client on the planet, it looks like it's 4 access points or 16 or whatever, right? Well, why does this make sense? Well, consider something like an airport deployment, airport in the original flyaway sense instead of the Apple sense. If you've got an airport deployment, you can have access points all throughout the airport, but in fact you might want to sell service through more than one provider, Boingo, Wayport, etc. So you could deploy multiple services per access point. Each one could have its own security, its own addressing, its own services. Right? So this makes it a lot cheaper for deployment.
Doesn't that go back to the bandwidth issues, particularly for 802.11b, because multiple access points interfere with each other?
That's true.
Because of the modulation mechanism.
Yes, that's true. There's a little bit of a gain and a little bit of a loss. Okay, of course you can apply the hammer approach, which is to say, oh, okay, well, I'm going to put another radio on my access point. One at 2.4 gigahertz, one at 5 gigahertz. That's one way to help, right? Another way is you're right. If I have 2 autonomous access points that are separate, that have no coupling, then my life is the hardest because each one of those access points could send a frame at the exact same instant, and I have to rely on collision avoidance. But if I'm one access point, I'm never going to do that. If I'm one access point, I have one transmit queue, and I'm going to serialize my access to the network in that means, right? So there's a little bit of a gain, but the loss, as you say, is the bandwidth, right? So yes, I have to. As a client, I can get service from that access point, but lo and behold, thanks to that serialization, that access point has to provide service to another BSS as well at the same time. Right.
So the available bandwidth is divided by the number of users.
Yes.
Which is exciting.
Yes. Okay. Right. So this is resources. If you're interested in figuring out how to attack web and all that kind of fun stuff, so the first resource here, I can't give enough credit to Bernard Aboba. So this is a really great site, for lots of fun reading for people like me. So it's some of these are in fact specs, but they're well written things of studies that Bernard and others have done on wireless, not just security. There's a lot of other things too. So, are there any questions?
You talked earlier about the approach that has a registrar.
Yes.
What happens when there's more than one registrar? What happens if the registrar is not initially present when the network is first brought up, and so forth? How are those situations handled?
Right. So there in fact must be a registrar. Okay. It's a requirement of the Wi-Fi Alliance that every AP be able to serve as a registrar.
Okay, so all APs
can, yes, but they don't have to. The example that I gave here was where the AP actually was an enrollee. Right? The registrar is on the bottom here. Right.
So if you have a digital camera and a printer, they can't talk to each other until you get an access point.
So you're implying that they're both wireless?
Yes.
Right. So that would depend on the vendor. Usually that's going to be true anyway, right? But in fact, if the vendor supports ad hoc networking, then you could, and And usually this would be a point-to-point solution. This would be, a Canon printer and a Canon camera may have a proprietary ad hoc mechanism to do it, right? But yes, you're right. So until you figure out that you need to go out and purchase that third piece of equipment, yes, you're stuck.
Yeah, I've had a bunch of grief in a situation where things are moving around and they get out of range of the access point and you can't talk anymore.
Well, they're thought to be in range of the BSS. Yes, so that's an implicit assumption, right?
Okay, one more question.
I missed a step on the handoff from one AP to the other. How does the IP level packet know that it has to get to the other AP instead of this one?
Yeah, so it's really not an IP level packet, but okay, so it's a layer 2. It's a 802.3 packet. What'll happen? Draw something here. Oh. Okay. All right. So I have AP1. Is this viewable? Oh, where's the camera going to be?
Right there.
Ah, okay, excellent. AP2. Right. This one. This wire? Wire's bad, huh?
Wire bad, wireless.
Bad wire. Okay. All right. So I have, the IEEE. If you haven't been able to tell by now, the IEEE calls these clients stations. So the station wishes to transition from AP1 to AP2. It's implied that there is some LAN that connects AP1 and AP2, right? And so once again, by LAN, this means that this is a broadcast medium, and that AP2 is reachable by AP1. All right. So now the protocol would be that okay. Well, so just to complete, so the protocol would be the station has to discover the presence of AP2 first, right? He would do that perhaps by going off channel and doing a scan, or he could use that TGK mechanism that I said, and AP1 could tell him that AP2 is nearby and it supports the same security, et cetera, et cetera.
Cell phone handoff for cells.
Yes, but
Say, which of you can hear me?
yes, the difference is that unlike the cell phone technology that ironically can and does make multiple connections to multiple cell towers at the same time, that's not what's going on here. The station never thinks that he's associated to more than one access point at a time. Now, he will multiplex his frames between these two access points, and that's according to the protocol, but neither the access points nor the station ever think that this guy is talking to more than one guy at the same time. Right? So.
Any other questions? Okay. Thank you very much, Kevin.
Oh, thank you.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.